Now let's start part 2 of this module. In this part, we are talking about how to incorporate effective problem-solving strategies within intensive intervention. If you remember, this module is all about different strategies that should be used within intensive intervention, and here we're going to focus on problem solving. So what we're going to talk about first is ineffective problem-solving strategies. So those strategies that we should not be teaching students. Then we're going to talk about different types of attack strategies. Every student should have an attack strategy to work through a word problem. So we're going to look at a few different ones, and then you can choose one that's going to work with your students. And then finally, we'll talk about the different schemas that are involved in different word problem structures. We'll talk about additive word problem structures, and then we'll talk about multiplicative word problem structures. Now, you might be asking yourself, well, why do we have to focus on problem solving? Well, I think that that's a pretty easy answer, but we want students to be able to reason about mathematics, to be able to engage in mathematics in a problem solving process. And another reason that it's really important to do this is that when students are looking at textbooks and when they're looking at questions on assessments, almost all of those involve some type of word problem solving. And so to demonstrate mathematical competency, students need to be strong problem solvers. So students need to be able to look at a problem just like this one. They need to be able to read it, understand what this graph is asking them to do, and then be able to read this question and provide a word problem answer. Now, I do have a note in this module, and probably actually have several notes as we work through these. Our focus is going to be on problem solving, and really I'm focusing on word problem solving. There are other types of problems that students are asked to solve that really are kind of like problem solving, but not in a word problem scenario. But almost all of the things that students solve in textbooks and almost all of the things that they see on assessments are through word problems, so that will be our focus here today. So what do we know about word problems? So students with mathematics difficulty, so those would be the students that you're going to be teaching in intensive intervention, those students often find word problem solving very challenging. And what might be some of the reasons for that? Let's look at a few of those now. One major reason that students have difficulty with problem solving is because of the reading of the problem. So students are presented with a bunch of text. They have to read that text and decipher that text to figure out what the word problem is asking them to do. Another thing that students have difficulty with in terms of problem solving is understanding vocabulary. So not only do I have to read all of this text, but I have to figure out what the vocabulary terms mean. And there's general vocabulary terms, and then there's also mathematical vocabulary terms. So what's what do students need to know there? There's a lot that they need to figure out when we're thinking about vocabulary. Students also have to find the relevant information, and word problems, it's not always that easy. These days we see lots of word problems with information embedded within charts and graphs. Sometimes it's embedded within pictures, and there's also a lot of irrelevant information. So numbers that students don't need to use, and many students with mathematics difficulty, they just see a word problem, they see all those numbers, and they just add all those numbers together. And they don't realize that some of these numbers I need, and some of these numbers we don't need. Other math difficulties other difficulties that students have with problem solving is interpreting charts and graphs. So what is this chart telling me? What is this graph telling me? And how do I use that information within a word problem scenario? And then we also have identifying the appropriate operation, and it could also be operations if it's a multi-step problem. So am I going to multiply in this problem, or am I going to divide, add, subtract? And then once I figure out that operation, how well do I perform that computation? So we've seen a lot of students do really well with all of these steps, and then you get down to here and they perform the computation incorrectly. So that's why this step here, this pink step here, that's why where we were talking about fluency earlier in this module, and later on we'll be talking about whole number understanding and rational number understanding. All of that is really important within this entire problem solving process. So let me just show you an example of a word problem here. So this is a word problem I showed just a few slides back. This comes from a standardized test item. I think this one is at 3rd grade. Yes, it is. All right, so we've got this problem here. So the first thing that students need to do is they need to read this problem. And look at all the text in this problem. We have text up here at the top. We have text here on the chart. Well, this is more of like a graph. And then we have text here in order to answer this question. So students have to read that text and they have to understand the vocabulary. Here there's general vocabulary, like delivers packages. Here there's math vocabulary, like I see the word total up there. So what does that mean when I'm asked about the total? And then the question has that same vocabulary term. Here we have the total number. What does that actually mean for me to figure out the answer to this problem? I have to identify the relevant information. So here this problem is about Monday and Tuesday. But look at this graph. There's a lot of irrelevant information on this graph. So I'm going to have to ignore Wednesday, Thursday, and Friday. I have to be able to interpret this chart and graph. So the number of packages goes up in units of 50. So what does Wednesday actually mean? What does Tuesday actually mean? I have to figure out those amounts from the graph in order to solve this problem correctly. And then I have to identify the operation. Here, if I'm asked about the total number of packages, I'm likely going to add numbers together to figure out that total, and I have to perform that computation correctly. Here, I'm adding 220 plus 100 and, what is that? 130. So with that, I may have regrouping involved, and so that goes into performing the computation correctly. Now let's think about what we know in terms of teaching problem solving. So at the beginning, I said we're going to talk about 3 things in this module. The first thing that I want you to remember is that we know one thing about teaching problem solving ineffectively, and that is to use keywords. And so we do not want to use keywords to teach problem solving to students. So I'm going to focus on that now, and then we're going to come back to numbers 2 and 3 and talk about those in a little bit. Now I want you to look at these posters right here. I'm actually going to move over here because I'm going to talk about this one the most. These are 2 posters that we will see in teacher classrooms, and they're super cute. Like, I love this one right here. Like, that there are words in mathematical symbols is like absolutely adorable. But here's the problem with this. For students with math difficulty, they just start to play a matching game. So they see a poster like this one here. And let's say they see that word total. So we already saw that word total in a word problem. If they see that word total in a word problem, what's right here next to that word total? A plus sign. And so they think like, oh, whenever I see the word total, I have to add. Now that's going to work in some word problem situations, but it's not going to work in all word problem situations. Let me show you exactly what I mean here. So here's one of our actually biggest word offenders in word problems that's used across a lot of different word problem types. Here's a story. Casey made $42 and Mandy made $37. How much money did they make altogether? Now, altogether is one of those words that a teacher has said, oh, look, whenever you see the word altogether, that means that you're going to add. So if I added $42 and $37 together, then I would get the correct answer to this word problem. But look at this one here. Casey and Mandy made $79 altogether. If Casey made $42, how much money did Mandy make? Now there's that word altogether. If my teacher has said, whenever you see altogether, that means you add, I'm going to find it on that list, I'm going to see that that list means addition, and I'm going to add those 2 numbers together. But the problem is when we add $79 plus $42, that does not give us the correct answer to this word problem. So here you can see the keyword strategy does not work. It might work for this problem, but it does not work for that problem. Here are a few other examples, and I won't spend a lot of time on these, but here more than as a keyword for subtraction works, but in this example, more than doesn't work. Here we see that twice works for a multiplication keyword, and then we see that twice doesn't work for a multiplication keyword. And finally, share and each will work for this division problem, but then share and each will not work for this division problem. So the whole thing about keywords is that students need to understand keywords. So I'm not saying that students shouldn't understand what twice means, that they shouldn't understand what altogether means, what per means, what equal means. Those are all really important math terms that students need to know. But don't tie those keywords to an operation. So when you're doing intensive intervention, you shouldn't ever say, well, whenever we see this, that means we do this, all right? So as we kind of go through the rest of this module, I think some of those things will come together for all of you. We do see keywords taught by teachers because it's actually probably the easiest way to teach word problem solving. but it might work within a grade level, but it has no staying power across the grade levels. And as we talked about in a previous module, we're always trying to help students understand this like continuum of mathematics. And so if we teach one thing that works right now, but it's not going to work next year and it's not going to work the following year, that's not helpful for students at all. All right? So what I want you to do is you're going to now do a workbook activity number 4. And here you're going to look at several different word problems. And I want you to identify what you might think are key words within each of those problems. There might be one keyword or 2 or 3, or figure out how many you think are keywords. And then I want you to look at that keyword and think, if I had taught a student how to use this keyword to solve this problem, how that might be problematic. Welcome back from workbook activity number 4. We just worked on number 1, and we learned about not using keywords tied to operations in order to teach effective problem solving. So you might be asking myself, well, what should I do, Sarah? Well, let's look at numbers 2 and 3. Now, number 2 says we need to teach students an attack strategy. So an attack strategy is something that helps students work through a word problem. And you probably, I would say believe it or not, but I think you'll believe it. But the hardest thing that students have a lot of times when they see word problems is actually knowing how to actually work through the word problem, doing the word problem step by step. So we're going to talk about attack strategies that can work with routine word problems. So a routine word problem is this example here. So here, Carol plays a ball game. She gets 7 points each time her ball hits a target. If she hits the target 5 times in a row, she gets an extra 25 points. So this is what we call a routine word problem. The students are given all of the information within the word problem, and they have to manipulate that information. But your attack strategy should also work for instructional word problems. So here's an example of an instructional problem where students are just given an instruction to do something. So here they have to figure out which 2 statements can be represented by this expression. So there's just an instruction, and then they have to figure it out. Now, the attack strategy should help students solve routine word problems, and it also should help students solve instructional word problems. And it's just giving them a guide for working through the problem step by step. So what are some of those different attack strategies? Well, I'm going to show you 8. Now, students should not know 8. They only need to know 1. So you need to choose the one that seems most appropriate for the student or students that you're working with. So I'll kind of talk through a few of these here. So here is an attack strategy called ridges, where students read the problem, make an I-know statement, they draw a picture, they make a goal statement, they develop an equation, and they solve the equation. So you can see that that would help a student work step by step through any type of routine or instructional word problem. Here's another one, and I've actually changed this one a little bit. With this one, I call R cubes. The first thing students should do is read the problem, and then they can circle the key numbers, underline the question, box the action words, evaluate the steps, and solve and check. Do notice where students might box the action words. That might say like, oh, Sarah, I'm teaching a keyword strategy. Not if you don't tie those to operations. Students need to be able to find those math words that tell us about what's going on in the problem. But as long as you don't say, oh, whenever you see this, then you do this operation, you're going to be okay. Here are a few other strategies. Here's one called RIDE. You can see that most of these are acronyms to help students work through the word problem. Here is one called STAR. In both of these, what's the first thing that students do? They read the word problem. Here's one that's for probably later elementary and middle school students. This one's called SOLVE. This one here called SIGNS. This is more of an elementary strategy that students might want to use. We also have this one here. This one in blue is from a middle school program called Solve It. So students do 6 things. It doesn't have an acronym, but it does work really well. So students read, paraphrase, hypothesize, estimate, compute, and check. And then this one here is the one that I'm probably going to use the most today, just when we're doing some examples. This one's UPS check. So students understand the problem by reading it, they make a plan, they solve, and then they check their work. And I'll use that one and demonstrate it a little bit here. But the idea with any of these attack strategies, let me kind of just go through them again. We've got ridges and R cubes, RIDE and STAR, SOLVE and SIGNS, the blue one and UPS check, is that it helps students understand what they're supposed to do whenever they see a word problem. And the primary thing that students don't do is read the problem. So what you'll notice about all of these attack strategies is the students read the problem first, and then it helps them work the rest of the way after they've done the reading of that problem. So you need to have an attack strategy. You need to have only one. It might make sense to just have the same attack strategy and use it with all of your students who are receiving intensive intervention. Or if you've got younger students and older students, you might have different attack strategies for those students. But you should look at the word problems that students are asked to set up and solve and figure out which attack strategy would make the most sense for students to learn and to use on a regular basis. So now we're going to leave number 2 behind and we're going to head to number 3. And this is another do when we're teaching word problems. And this is that we should teach students about schemas. Now, a schema is basically the structure of a word problem. So instead of describing a word problem at a very superficial level based on the operation, we don't want to do that. I've been in teachers' classrooms where they will say, today we're working on addition word problems. Well, how do the students know that it's an addition word problem? You're just telling them, all right? So it's not really helping the students reason or think about word problem solving at all. Instead, we want to help the students have a much deeper understanding of problem solving. And that is by teaching problem solving by schemas. Now, there are additive schemas. Additive means addition and subtraction, so the students would use those operations to solve the word problems. And then there are multiplicative schemas, where students may multiply and divide to come up with the word problem answer. But the schemas here focus on the structure, the underlying structure of the word problem. And with the additive problem types, there are 3 schemas: total, difference, and change, and I'll talk about those in just a minute. And then with the multiplicative word problems, we have equal groups, comparison, and ratios and proportions. And I'll talk about those in just a little while. So let's go ahead and talk about the additive word problems. So we're going to talk first about total problems. I'm going to talk about it first because it's kind of the easiest for me to introduce, and it kind of sets up all of our other word problem schemas. But that doesn't necessarily mean that you would teach it first. So you want to figure out well, what word problems are the students working on, and then teach the schemas that go along with those different types of word problems. Now in total problems, we have parts, and we put those parts together into a total. Let me show you some examples of what that looks like. So here, Emily saw 4 cardinals and 5 blue jays. How many birds did Emily see? So we have 2 parts in this problem. We have a part about cardinals, and we have a part about blue jays, and the question is asking us, how many birds did Emily see? So students might set up an equation like 4 plus 5 equals question mark. But these are also total problems. Emily saw 9 birds. If 4 of the birds were cardinals, how many were blue jays? Now this problem is also about cardinals and blue jays, so we have 2 parts. But in the second problem, we're given the total. We're given that Emily has 9 birds, we're given one of the parts, and our job is to find the other part. And the same thing with this last question here. We're given the total of 9 birds. We know that 5 of those are blue jays. How many were cardinals? These are all total problems because we have parts put together for a total. Sometimes one of the parts might be the missing information, and sometimes the total might be the missing information. It doesn't matter where that missing information is. If the problem is about parts and a total, it is a total problem. Now, how do we help students set up and solve these total problems? Well, there's 2 really good ways to help students organize information from total problems. One is that you can use a total equation. So here we could use P1 plus P2 equals T. So that's part 1 plus part 2 equals the total. And that would help us organize the information from a total problem. We could also use a graphic organizer. Here's just a pretty simple one, just square plus square equals square, but that's part plus part equals the total. So now let's look at a word problem. I'm going to solve one, and then you'll have a chance to look at a few of these later. But I'm going to solve this word problem as I was teaching it to a student. So I'm going to move over here, and the first thing I do is that I see a word problem. I always like to describe word problems with students as a mix of numbers and words. So whenever I see that mix of numbers and words, I've got a word problem on my hand. And the first thing that I do is I always write my attack strategy. And in fact, I'm going to try to move this down a little bit lower so I don't go over the word problem here. We'll go right there, UPS check. Now this is the attack strategy that I'm going to use today. This doesn't necessarily mean that this is the one that you're going to use. You just have to have one of these. And remember, this stands for understand, plan, solve, and check. So I'm going to U this problem. I need to understand this problem, and I can only understand this problem by reading it. Ella and Susan planted 12 flower seeds. Ella planted 3 flower seeds in 2 trees. How many flower seeds did Susan plant? I need to also understand this problem by figuring out what I need to find. And in this problem, I'm talking about flower seeds. So I'm going to come up here and I'm going to underline flower seeds just like that to help me remember that I want to really focus on the numbers that deal with flower seeds. And I think I've got a pretty good understanding of this problem, so I'm going to check it off to remind myself that I've already done the U of UPS check. Now it's time to focus on this P. That stands for making a plan. I always ask students to make a plan by thinking about the schema of the problem. Now we've only talked about total problems, and it says total at the top of this slide, so this is likely a total problem. But I always ask students this: is this a total problem where parts are put together for a total? Is this a difference problem where amounts are compared for a difference? Or is this a change problem where one amount increases or decreases? Now this is a total problem because we have parts put together for a total. We've got Ella's seeds and Susan's seeds, and we're putting those together for a total. So I'm going to solve this as a total problem, and on this example, I'll use my total equation to help me solve this problem. And that is P1 plus P2 equals T. So we've got our parts and our total. I've got my plan. Now it's time to move down here to S. It's time to solve it. Ella planted 12 flower seeds. 12 is a number, so we stop. 12 talks about flower seeds, so I probably need it in this problem. And does 12 tell me one of the parts or the total? Hopefully a student would say, oh, it tells you about the total, so I'm going to check off that 12 so I don't use it again, and I'm going to write it underneath my letter T right there. Notice one thing is that I do not have to fill this equation in left to right. Whenever I figure out I've got some word problem information that I need, and whenever I figure out where it's going to go in the equation, I go ahead and plug it right in, all right? Now I'm going to continue reading. Ella planted 3 flower seeds. 3 is a number. I'm going to use that because it talks about flower seeds. I'll check it off so I don't use it again. And I ask students, does 3 tell us about one of the parts or the total? 3 tells us about one of the parts, so I'll put it underneath P1. Now I've got some information up here, 2 trees. I'd say 2 is a number, so we're going to stop, but 2 doesn't talk about flower seeds, it talks about trees. So that is irrelevant information, and I'm going to cross that out. I do not need that information. Probably wouldn't always encourage students to cross it out so violently, but now we've got that 2 trees crossed out, and I'm not going to confuse it and put it into my equation. And then finally, how many flower seeds did Susan plant? We don't know that. I'm going to mark my missing information this time with a question mark. And now I'm going to solve this problem. I'm going to put in my plus sign and my equal sign, and now I'm going to move over here to solve this problem. Now, some students might solve this problem by counting up. They might be, well, 3 plus, and they'd say 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 3 plus 9 is 12. So I might be able to add to solve this problem. Other students might subtract to solve this problem. 12 minus 3 equals 9. So here I figure out that my question mark is 9, and I don't ever like to leave word problem numbers by themselves. I'm going to look up here and use this flower seeds as my label, because after all, the question was asking me how many flower seeds did Susan plant, and our answer is 9 flower seeds. And so I've solved this problem, and how do I check my work? I can go ahead and plug in that 9. 3 plus 9 does indeed equal 12. So I'm going to double check that I have solved this word problem. Now before we move on to the next slide, I want to talk about this part right here. All right? Earlier I talked about keywords and not using keywords tied to operations. And when we think about teaching problem solving, we want to teach the problem solving by the deep structure of the problem. If I teach problem solving just by operations, by saying, this is an addition problem, this is a subtraction problem, that doesn't really help students reason about the word problem. And in fact, is this an addition problem? Not really. Is it a subtraction problem? Not really. I might have added to solve this problem, whereas someone else may have subtracted to solve the problem. So you cannot define word problems by their operation. Instead, you have to look at the entire word problem and figure out the structure of the word problem. So this is a total problem. This is the structure. It's parts put together for a total. And now we'll go ahead and look at difference problems. Now we're going to talk about the next additive schema, and that is the schema of difference. And here I have a greater amount and a less amount, and I compare those amounts for a difference. Some people might call those the bigger and smaller numbers. So here are some examples of difference problems. Let's focus on this first problem up here about Sinead and Amanda. Sinead has 9 apples and Amanda has 4 apples. How many more apples does Sinead have? Or we could ask, how many fewer apples does Amanda have? Now in this problem I have 2 amounts. I have an amount that is greater and an amount that is less, and we're comparing those amounts for a difference. So this is a difference problem. Now in this second example, Sinead has 5 more apples than Amanda. If Amanda has 4, how many does Sinead have? So here we're given the difference. 5 more apples tells the difference between Amanda's apples and Sinead's apples. Then we're given Amanda's amount, and we have to figure out Sinead's amount. And on this last one, Amanda has 5 fewer apples than Sinead. Sinead has 9. How many does Amanda have? So the same thing, we're given the difference, and we're given the amount that's greater, and here in this problem, we're asked to find the amount that's less. Now these look like 3 different problems, but they are different problems, but they all have the same structure. They are all difference problems because we have a bigger amount and a smaller amount, and we're comparing those amounts for a difference. So what are some of the ways that we can help students set up information from difference problems? Well, you could use a difference equation here, b minus s equals d. We also have a graphic organizer. The circle minus the circle equals the square. Let's look at this word problem here, and this time I'll use the graphic organizer to set up this word problem information. So I see a mix of some numbers and words, so that means I'm going to use my problem-solving strategy, and that is U, P, S, check. I always like to write it along here on the side so I can remember, first I do this, then I do that, then I solve it, and then I check it. I need to understand this problem, understand it by reading it. Zach wrote 49 words in his math journal. Pedro wrote 74 words. How many fewer words did Zach write than Pedro? Another part of understanding it is kind of figuring out, well, what do I need to figure out in this problem? I need to figure out how many fewer words Zach wrote than Pedro. So I'm going to underline the word words to help me focus on all the numbers that talk about words. Now, one thing that I have seen teachers do is they'll say, oh, whenever you're doing problem solving, underline the question. What will students do? They will underline the entire sentence with a question mark. Or better yet, they'll underline the entire problem because it does seem like a question. Now that shows that your students are pretty good at drawing horizontal lines, but it doesn't tell you anything about their understanding of the word problem. So here, just be very, very judicious in what you ask students to underline, what you model in terms of your underlining, and what you ask students to practice in terms of their underlining. So I've got an understanding of this problem. Now I'm going to make a plan. Is this a problem where parts are put together for a total? Is it a problem where amounts are compared for a difference? Or is it a problem where there's a change? We've got one amount that increases or decreases. Now this is not a total problem because I'm not taking parts and putting them together for a total, but it is a difference problem because I've got Pedro's words and Zach's words, and we're comparing the difference between those. So I'm going to solve those with a graphic organizer here. I'm just going to do circle minus circle equals square. And if I wanted to label these, I could, but I'm going to have my bigger amount here, my smaller amount there, and then I'm going to have my difference down here. So I've got my plan, and now it's time to solve this problem. All right, so I start at the beginning. I'm going to stop anytime I see a number because I may need that for my word problem answer. Zach wrote 49 words in his math journal. So 49 is a number, so we're going to stop. 49 talks about words, so I'm going to check off that number, and now I'm going to think about where I'm going to use that. So Zach wrote 49 words in his math journal. Pedro wrote 74. If Zach wrote 49, that's going to be the smaller amount. So I'm going to put it in this box here right there that represents the smaller amount. Now I'll keep reading. Pedro wrote 74 words. 74 is a number, so I'm going to stop It talks about words, so I'm going to use it in this word problem. And if Pedro's amount, we already talked about that is the bigger amount, so I'm going to put it here in the box for the bigger amount. And then the question asks, how many fewer words did Zach write than Pedro? I'm not sure, so that's our question mark here. So now I've got to solve this problem, not done just yet. So I may subtract 74 minus 49. If I do my mathematics here, I end up with an answer of 25. So some people may subtract to figure out this answer. Other people could add to figure out this answer. 49 plus 25, since I already knew the answer, there is 74. So again, it's not a subtraction word problem. It's not an addition word problem. It is a difference problem. So 74 minus 49 equals 25. I'm kind of checking my work there. And my question mark is 25. And I always want to label for my word problem number. I'll look right up here what I underlined earlier, 25 words. So if I ask the student, how many fewer words did Zach write than Pedro? My answer is right here, 25 words. 74 minus 49 is 25. I checked my work, and now it's time to look at change problems. All right, now let's think about our last additive schema. This is the schema of change. And these are actually the easiest for students to pick up on because they're really easy to visualize. They occur over time, so it's quite easy for students to see things like, oh, they cleaned their room, or they ate some hot dogs, or they earned more money. So here we have one amount, and that amount increases or decreases. So look at these examples here. Shanna had $4. Then she got $3 for cleaning her room. So she started with $4, and then that amount changed because she got more money. And then the question asks, how much money does Shanna have now? Now we could be asked that. It's kind of a classic change problem, but we might be asked these second and third examples. Shanna has $4. Then she earned some money. Now Shanna has $7. How much money did she earn? So in this problem, I'm given the start amount and the end amount, and we have to figure out that change. And then in the final example, Shanna had some money, then she made $3 for cleaning her room, and now she has $7. How much money did Shanna have to start with? So they were given the change and the end amount, and we have to figure out how much money she had to start with. So there's change where we have an increase, and there's also changes where we have a decrease. So here are some examples of that. Michaela had $9, then she spent $2 on candy, so her amount of money is changing. How much money does she have now? Or Michaela has $9, then she spent some money, now she has $7. How much money did she spend on the candy? Or Michaela had some money, then she spent $2, now she has $7. How much did she have to start with? In all of these, we have one thing, it's money. And that amount of money is changing. It's either increasing or decreasing. Sometimes we're asked about the start amount. Sometimes we're asked about those changes. And other times you're asked about the end amount. So how much does she have after an increase, or how much does she have after a decrease? Now, just like with total and difference problems, we have change equation. Here we have our start plus or minus, so plus with an increase, minus with a decrease. The C, the change, equals the end amount. So ST plus or minus C equals E. And we also have this nice change graphic organizer here that kind of shows the change over time. So let's look at one of these change problems. I'll solve this problem and kind of show you how we would work through this one. I see a mix of the numbers and words. That's a word problem, so I'm going to UPS check this problem. I understand the problem by reading it. A bus had 13 passengers. At the next stop, more passengers got on the bus. Now there are 28 passengers. How many passengers got on the bus? This problem is about passengers. And I'm going to take this word passengers here, and I'm just going to underline it just like that, so I can really focus on the numbers that talk about passengers. Now, one thing that kids may ask is like, oh, do I have to underline passengers here? Should I underline passengers here? Should I underline passengers here? They can, but really, just by underlining it once, I'm now cued into this idea of passengers, and I have an understanding of this word problem. Now let's make a plan. Is this a total problem where parts are put together for a total? Is it a difference problem where amounts are compared for a difference? Or is this a change problem where one amount increases or decreases? Now this is a change problem not only because it says change at the top, but it's a change problem because we have this number of passengers on the bus. And those passengers, the number changes because more passengers get on the bus. So that amount increases. So this is a change problem. And I'll use I'll do a combination here. I'll use my graphic organizer of a change problem. So a nice circle to another circle to a final circle. And if I wanted to label these, this will be my start amount, my change amount, and my end amount, okay? And you know, it's a little hard to see that with my marker, so I might just change markers right now. All right, now we've got our plan. We're going to solve this as a change problem. So now let's go ahead, start at the beginning, read, find all the numbers that deal with passengers, and figure out how they fit into this change schema. A bus had 13 passengers. 13 is a number. I'm going to check it off because it talks about passengers, and I need to use that number in this story. So does 13 tell me the start amount, the change amount, or the end amount? It tells me how many passengers were on the bus at the beginning, so I'll write 13 in the box that says start. Now at the next stop, more passengers got on the bus. It doesn't tell me how many more, so I'm not sure. I'll mark that with a question. I don't know the change in the number of passengers. But if I keep reading, now there are 28 passengers. 28 is a number that talks about passengers, and I'll check it off so I don't use it again, and it tells me the end amount, because now there are 28 passengers on the bus. So now I'm going to solve this problem. I'll kind of go over here to do that. Let's see, I could do 28 minus 13. Do the mathematics here, and I find that there are 15 passengers on the bus. I could also add, and you know, one of the strategies I'll show you is adding up. So 13 plus 7 gets me to 20, and I need to get all the way to 28. 20 plus 8 gets me to 28, and I add these together. 7 plus 8 is 15, so the difference between 13 and 28 is 15. So it doesn't matter if I subtract, it doesn't matter if I add. Here I figure out that my question mark is 15, and I need a label for that, so I'll go over here. What did I underline? What did I say that this problem was about? I say it's about passengers, so I'll write that in there. And then finally, I've got it solved. I want to check this. So 13 plus 15 does equal 28, or students might subtract 28 minus 15 does equal 13. So I'm going to double check that problem because I've checked my work, and we have solved this change problem. All right, now that you have learned all about the additive schemas, it is your turn to figure out what the different schemas are of different types of additive word problems. So now you're going to work on workbook activity number 5. There I want you to read the problem, identify the schema. So is it a total problem, a difference problem, or a change problem, and then solve the problem using the schema. So let's review the answers for workbook activity number 5. Let's look at problem number A. I'm not going to go through this entire problem, but I am going to focus on the question. And here the question says, how many minutes did Ryan spend doing homework Tuesday and Thursday combined? So if we're thinking about combining Tuesday and Thursday, this, problem A, is a total problem. Let's look at problem B. Here, how many sheep does Ramon have in the other field? Well, here we're given the total number of sheep and the sheep in one field, so this is also a total problem. This is a total problem where we're given the total, which is 815, and we're given one of the parts, and your job is to find the other part. So B is also a total problem. Let's look at problem C. Here we're given this scenario where the students are taking different numbers of pictures. And here the question says, Ella took 8 more pictures than Ted. How many more pictures did Ella take than Mary? Anytime we're comparing two different amounts, that's a difference problem. So problem C is a difference problem. Now let's look here at problem D. Rosa had some stickers, then she gave some to one of her friends. Now she has some stickers left. The question is, how many did she have to start with? This is talking about a change in the number of Rosa's stickers. So problem D is a change problem. And then finally problem E. There are 425 boys and 510 girls. How many more girls are there than boys? This is a problem where we're comparing two amounts. We're comparing the boys to the girls. So problem E is a difference problem. All right, so we have talked about the additive schema of total, difference, and change. Now it's our opportunity to learn about the multiplicative schema. So we're going to talk about equal groups schema, the comparison schema, and then the ratios, proportions schema. So let's talk about those equal groups schema first. So in an equal groups problem, we have groups, and then there's an equal number within each of those groups, and we put all of those together for a product. So what do some of those problems look like? Mark has 2 bags of apples. If there are 6 apples in each bag, how many apples does Mark have altogether? So imagine it. I've got 2 bags of apples. 6 apples in this bag, 6 apples in this bag, and then how many apples does Mark have altogether? So there I've got 2 groups with 6 in each group, and we have to figure out the product. But we can also think of equal groups problems written in this way. Mark has 12 apples. He wants to share them equally among 2 friends. How many apples will each friend get? So there we're given the groups and the product, and we have to figure out the number that goes in each group. Or Mark has 12 apples. He puts them into bags containing 6 apples each. How many bags did Mark use? So in that question, we're asked about the groups. Now in some of these problems, we might multiply to solve the word problem, and some of the problems we may divide. It doesn't matter. It's just like the additive problems. I'm not going to describe them as an addition problem or a subtraction problem. Here, with the multiplicative problems, I'm not going to describe them as a multiplication problem or a division problem. That's kind of a superficial way of describing these word problems. Instead, I'm going to describe these as by their schema. And here, the schema is an equal groups schema. So let's look at this problem here. I see a word problem, and what am I going to do every time I see a word problem? I'm going to use my attack strategy. And the attack strategy that I like to use most is that UPS check. Now, the painter bought 56 cans of paint to paint 8 different houses. How many cans of paint will the painter use on each house? So in this problem, I'm focusing on these cans of paint. So I'm going to underline that to help me figure out the understanding of this problem. Now I'm going to make a plan. Here I've got to ask myself some different questions. Is this an equal groups problem where I have groups with an equal number within each of those groups? Is this a comparison problem where I have a set multiplied a number of times? Or is this a ratios or proportions problem where if this is to that, then this is to that? Now we haven't talked about those other 2 just yet, but I see that this is an equal groups problem because I've got houses, so those are my groups. And I need to figure out the number of cans of paint for each of those houses. So I have to figure out the number within each group. So I'm going to solve this problem. I'm going to talk about my groups times the number in each group, and I multiply those for a product, all right? We can use any different type of equation or any graphic organizer to help us organize this work. So I've got my plan, and it's now time to solve this problem. The painter bought 56 cans of paint. 56 is a number that talks about cans of paint, so I'm going to use it. And 56, it doesn't tell me the number of groups I have. It doesn't tell me the number within each of those groups. But 56 tells me how many cans of paint I have altogether, or my product. I keep reading. He's going to paint 8 different houses. 8 tells me about the groups that I have. So I check that number off and write it here underneath G. And then I have to figure out how many cans of paint are used with each house. There, I'll use a question mark. Now I'm going to solve this problem. I write in my multiplication symbol and my equal sign. And I could solve this in a variety of ways. I'm going to start to solve this algebraically. We draw a line straight down from the equal sign. And now I'm going to balance the 2 sides of this equation. So I'll divide by 8 on both sides. And if I do that, my question mark equals 7. And remember, I don't want to leave this 7 by itself. I'm always going to use a label for this. What were we asking about? We were asking about the cans of paint for each house. So I'll put cans as my word problem label. And so I've got my problem solved. And if I wanted to go back and check, I could say 8 times 7 does it equal 56, or 56 divided by 7 equals 8. Now let's look at the next type of problem. All right, we just talked about equal groups problems. Let's talk about the next multiplicative schema, which is the schema of comparison. Here we have a set multiplied a number of times for a product. So here's the example that we see most often when we actually see this schema in different textbooks and on different assessments. Jill picked 6 apples. Mark picked 2 times as many apples as Jill. How many apples did Mark pick? Now we also could see the word twice put in there. Mark picked twice as many apples as Jill. So here we have a set. We have Jill's 6 apples. And then that set is multiplied a number of times. So how many times more apples did Mark pick than Jill? When we look at comparison problems in the elementary grades and the middle school grades, they're most often this type of question. You might see these other 2 examples, but I haven't really come across them in the wild, so I don't really want you to focus on them with your students, but you really should focus on this first type of comparison problem because students will be asked to set up and solve that type of problem. So let me show you this problem, and this one I'll just do a little bit different because it's actually going to involve some rational numbers here. So I see a word problem, and I need to UPS check that problem. And so I understand something by reading it. The playground at the new school is 2,140 square feet. The playground at the old school was 856 square feet. How many times larger is the new playground? So I have to figure out how many times larger. So I'm focused on the times. That tells me I'm probably going to be doing something comparison. But I also may want to underline square feet because this problem is really about the square feet of the 2 different playgrounds. So I have an understanding of this problem, and now it's time to make a plan. Is this an equal groups problem where I have groups with an equal number within each of those groups? Is it a comparison problem where I have a set multiplied a number of times? Or is it a ratios and proportions problem, which we'll talk about next? This is a comparison problem because I'm comparing the square feet of the old playground to the square feet of the new playground. So here I have a set multiplied a number of times, so set times equals the product here. So I got my plan, and now it's time to solve this problem. The playground at the new school is 2,140 square feet. That tells me about square feet. I'm going to use that number. And it tells me how many square feet there are at the new playground. So that's kind of my 2,140 here is my product. The playground at the old school was 856 square feet. So that's a number that I'm going to use. I'll check it off. And that tells me the original set. So the original was 856 square feet. And remember, my question asks me how many times larger is the new playground. I'm going to put in my multiplication sign and my equal sign. I'm going to draw a line down here to balance both sides of the equation. I'm going to divide 856 from both sides. And because I'm super smart, I'm not even going to do the math. And because of time, I know that 2,140 divided by 856 is 2 5/10 times larger. We would never say 0.5. Remember when we were talking about math language. And it's 2.5 times larger than the old playground. So I'd put my label on it just like that. All right, now let's talk about our last multiplicative schema here. This is a schema where we can think about comparing ratios, proportions. We can also think about unit rate and percentages. There's actually a lot that we can do with this multiplicative schema. But here we always have 3 bits of information, and we're trying to figure out a 4th bit of information. So if this set is to that set, then this set is to that set. So let's look at what some of these examples look like. So here I have a mix of numbers and words. That is a word problem. So I'm going to UPS check this problem. So Sylvia used 2 cans of icing to ice 24 cupcakes. How many cupcakes can she ice with 7 cans of icing? So in this problem, I'm worried about the cans of icing, so I'm going to underline that. And I'm also focused on these cupcakes. So how many cupcakes can she ice with these cans of icing? So now I have an understanding of this problem. I'm going to make a plan. Is this an equal groups problem where I have groups with an equal number within each of those groups? It is a comparison problem where I have a set multiplied a number of times. Or is this a ratios and proportions problem where if this set is to that, then this set is to that? Here I do have, if this set, so if 2 cans of icing ice 24 cupcakes, then how many cupcakes can she ice with 7 cans of icing? And we'll use our ratios and proportions graphic organizer. This comes from Asha Jitendra and her research team. So here I'm just going to draw a circle, arrow, and a nice little rectangle there. And now I've got my plan, and I'm going to fill in this graphic organizer. So Sylvia used 2 cans of icing. So I'm going to check off 2 because it tells me about cans. And while I'm here, I'm going to go say that those 2 cans ice 24 cupcakes. So if 2 cans ice 24 cupcakes, then how many cupcakes can she do with 7 cans of icing? So I'll cross off that 7. So 7 cans of icing, ice, question mark, cupcakes. Now I'm going to set this up in an equation form. 2 over 24 is the same as 7 over question mark. And here I could cross multiply. 2 times question mark equals 7 times 24. Through the magic of all that is math, I know that this is 168, and this is 2. And then I divide by 2 on both sides, and question mark equals 84. And I need a label for this. I have to figure out, does it talk about cans or does this 84 talk about cupcakes? Here it does talk about cupcakes, so I'll write cupcakes as my label. And so how many cupcakes can she ice with 7 cans of icing? She can ice 84 cupcakes. Now I'm going to go ahead and leave this up here because I'm just going to quickly have you think about workbook activity number 6. So in this activity, you're going to look at the multiplicative schemas. And here, just like you did with workbook activity number 5, you're going to read the problem, then you're going to identify the schema, and then you're going to solve that problem using the schema. Now this whole workbook activity is focused on the multiplicative schema. So be thinking about equal groups, comparison, and ratios and proportions. Let's review workbook activity number 6. Let's look at problem A. Here, Jim uses ribbon to make bookmarks, and he has 9 feet of ribbon and uses 1/3 of a foot of ribbon for each bookmark. Our question asks, what is the total number of bookmarks that Jim can make with all 9 feet of ribbon? This is an equal groups problem where I have to figure out the number of groups or the number of bookmarks. So if I was writing this equation, and I could go ahead and write this down here, I don't know the number of groups, but I do know that each group has a value of 1/3, and then altogether we have 9 feet of bookmarks. Sorry for my blue squeaky marker, but this is an equal groups problem. While I'll erase that, we'll go ahead and flip to problem B. Here, Scott is reading a book that is 172 pages, and then Melanie is reading a book that is 3 times as many pages as Scott's book. Whenever we have that comparison going on, comparing Scott's book to Melanie's book, that is a comparison problem. So problem B is a comparison problem. In problem C, Lindsay has 18 flowers and she plants them in 6 flower pots. Each flower pot has the same number of flowers. How many are in each pot? This is your very classic equal groups problem that comes through as an equal shares. So again, I'm trying to figure out how many are in each group. So I have 6 flower pots, and then I have to figure out the number within each group, and we have 18 flowers altogether. So problem C is an equal groups problem. What about problem D? A water dispenser contains 512 fluid ounces of water. What is the total number of 8 fluid ounce cups that can be filled from the dispenser? Now this can also be thought of really as an equal groups problem because I want to figure out the total number of groups if each has 8 fluid ounces in it, and I have 512 fluid ounces total. And then we get to problem, so D, equal groups. Then we get to problem E. Isaiah put 301 floor tiles in 7 rows. If each row had the same number of tiles, how many did he put in each row? We could think about this as an equal groups problem. So if students say it's an equal groups problem and solve it as such, that's totally cool. We could also think about a problem like this as a ratios and proportions problem. And I'll show you a little bit what I mean right here. So if there are 7 rows, and I want to figure out, well, like how many did I put in each row? So 7 rows has 301 tiles. Then I could figure out, well, 1 row has how many tiles. So I could set up the relationship in this way, so 7 is to 301 as 1 is to question mark. So problem E is really an equal groups problem, but can also be solved as a ratios and proportions problem. All right, welcome back. We are almost to the end of this part of the module. But before we get to the very end and you get to do all the fun discussion board and journal activities, I want to talk about a few other considerations. So one is that many word problems actually combine schemas. So here is an example word problem from a standardized assessment. And if we look at this word problem, Jonas has 18 packages of gum that contain each package has 5 pieces. Then he gives 16 pieces of gum to his friends. Here we're asked which number sentence helps figure out the word problem answer. But when I would solve this problem with students, I won't do the whole thing here, but I would actually set this up maybe in like kind of a T-chart here. So first, Jonah has 18 packages of gum that each contain 5 pieces. So first I'm going to solve that as an equal groups problem. So 18 times 5 equals question mark. And then I need to figure out the difference. So he gives 16 oh, that's actually a change problem. I figure out the change here. So we have how many pieces of gum he had total. We subtract 16 from that. We have a decrease there. And then we have a new question mark that we have to figure out there. So this just helps the students organize that information in a meaningful way. Now I'm going to go on to erase this here because then we're going to go on to our next problem, which is actually this same problem again. So my other reminder here is that sometimes students don't answer word problems with an answer, all right? Many times on different types of standardized tests, students actually have to show us like an equation, or maybe actually like which graph represents this word problem information. So back to this problem about Jonas, here the response is not, can you figure out the answer to this problem? The response that the student is supposed to provide is actually like, which of these equations represents what's going on in the word problem? So being able to teach students not only to like set up and solve these word problems, but to understand how equations can be used to represent the word problem information. We also have to remember, and we kind of talked about this at the beginning, is that not all word problems are routine word problems. So when we are talking about the schemas, those help us solve routine word problems. Word problems where we're given information in the word problem and we manipulate that information within that scenario. We also have a lot of instructional word problems. I already showed an example of one of these earlier, but here are a few other examples. Here the instruction is just to figure out which of these statements is true. And here the instruction is what number makes these fractions equal. Now these attack strategies that we talked about, so ridges, star, R cubes, ride, UPS check, those should also be able to be used with these instructional word problems. So if I was like UPS checking which statement about the angles is true, I would understand it by reading it. I would make a plan as to go through each of these and see if they are true or false. I would solve the problem, and then I would go back and check my work. So you can see how that attack strategy doesn't just work with word problems where we're manipulating those numbers, but it also works with word problems where we're given a set of instructions. Now at the end of this module, you're going to participate in a discussion board activity about attack strategies. And so with your discussion board activity, I want you to think about the effective attack strategy that you might want to use during intensive intervention. And I'd like you to create your own poster that you could use. So it could be set up like in your classroom or during your small group or individual instruction that could show students the steps to your attack strategy. You're welcome to make a poster of one of the attack strategies that I shared. You're also welcome to come up with your own attack strategy. Just remember, the first thing that it should always have is that the student should read the problem. And then you'll share these attack strategies with your colleagues, and so then you'll have a whole bunch of different examples of attack strategies that people might use during problem-solving instruction. Now before we break there and you get to making your own attack strategy poster, let's go over our checklist from this module. So our whole question here was, how do you incorporate effective problem-solving strategies within intensive intervention? So remember, do not use keywords tied to operations. Should students know keywords? Yes, but never say, whenever you see altogether, that means you add. Don't say examples like that. So what should we do? Have an attack strategy. We just talked a lot about those and we saw a lot of examples of those today. Teach students schemas. That gets to the underlying structure of those word problems. It helps them actually understand what the problem is about. And then a few other things that I hope kind of go without saying. Do explicitly teach problem solving. So this is where explicit instruction with lots of modeling and practice opportunities comes into play. Problem solving instruction needs to be provided regularly. Many teachers leave this as kind of like the last activity of the day, or they go at it once a week. But mathematics competency is judged through your problem-solving experiences and your problem-solving prowess. So we need to give students as much practice with problem-solving as possible. So I would say several times a week, you need to be setting up and solving word problems with your students. And then also be reflective about what your students are asked to set up and solve. So I went over all the additive schema and all the multiplicative schema, but that doesn't necessarily mean that your students are going to see all of those schemas all of the time. So look at what students are asked to solve in their textbooks and on different types of assessments, and practice the schemas that students will encounter regularly. Now, before we break, I do have a video of intensive intervention with a problem-solving program, and here we're just going to watch the tutor talk about the different schemas with a student. You're going to notice this tutor, she's going to be very, very precise with her mathematical language. She's going to ask the student regularly to provide feedback to her, and then she's also going to use her hands to use the gestures for the different additive schema. So watch that video, and I'll be right back.
Now let's go through our problem types. First we have total. So let's do it together. In total problems, we ask ourselves, are two or more parts put together for a total? Now you do it. Exactly. And what's the total equation? You got it. Now let's do difference problems. When we have a difference problem, we ask ourselves, are two amounts compared for a difference? You do it. Perfect. And the difference equation is? You got it. And the compare words are? Right. And there's a one compare word that is in another type of problem. Which one is it? Yeah, but which word is it? More. That's right. So let's go over change problems. When we have a change problem, we ask ourselves, is there a start amount that increases or decreases to a new amount? That's right. Now you do it. You got it. And when the start amount increases, what's the equation? You got it. And when the start amount decreases? You got it, dude. Here, I'm going to give you a coin just for that awesome review. Let's take a look at 8.
All right, thank you so much for playing with me and with word problems with this part of the module. Before you head to your discussion board task about making your different attack strategy posters, I also want you to engage in a journal entry with this part of the module. So I want you to reflect upon any previous instruction that you have provided about word problems, or maybe instruction that you've seen other people provide about word problems. And I want you to be reflective and think, what practices might you discontinue? What practices might you continue? And then what are some of the most important takeaways from this part of the module? So just be reflective of all we've learned, because it's been a lot. We've learned a lot about problem solving. But it's really important that students have strong understanding about how to solve problems in an effective way. So I want you to be reflective here so that then you can provide really good intensive intervention related to problem solving.